Reducing atherogenic burden is one of the greatest challenges for today's physician facing the epidemic of atherosclerosis. Fortunately, research is yielding enormous insights to meet this challenge. Recent decades of study have proven that lowering LDL cholesterol reduces cardiovascular disease. Yet still, many cardiovascular events occur without significant elevation of LDL cholesterol. Newer data are revealing significant atherogenic potential in lipoprotein particles other than LDL. In some circumstances, the composition of any of the lipoprotein particles can be altered, allowing participation in the atherogenic process. Furthermore, it has been shown that hypertriglyceridemia is a marker for the existence of such atherogenic particles. Hypertriglyceridemic patients at risk exhibit elevated triglycerides and low HDL cholesterol. This profile is often associated with the metabolic syndrome and diabetes, resulting from overnutrition, obesity, and physical inactivity, and leading to premature atherosclerosis. The epidemic of metabolic syndrome is expanding the high-risk patient population and has led to changes in therapeutic guidelines. In even newer research, the focus for reducing the atherogenic burden is moving away from the plasma and into the artery wall, specifically to the macrophage. Of great significance is the discovery of the receptors and transporters responsible for getting cholesterol into and out of the macrophage. These advances in scientific understanding are allowing yet another avenue for achieving our therapeutic goal: reduction of cholesterol in the macrophage of the artery wall. The treatment of dyslipidemia is continuing to evolve from a science previously grounded in the measurement of the lipid cargo, that is, total cholesterol and triglycerides in the plasma, to a science focused on the more sophisticated determination of the functionality of lipid transport pathways. Research is revealing complex interrelationships between lipoprotein particles, receptors, and enzymes necessary for functional lipid distribution. To understand these processes, let's first take a look at the dynamic structure and composition of the various lipoprotein particles, which serve as the transporters of lipids from sites of absorption or synthesis to sites of utilization, or in the case of atherogenesis, sites of accumulation. Lipoproteins function to package insoluble lipids for transportation in the blood. Two essential but distinct lipid types are carried primarily in the lipoprotein core. One type, the triglycerides, is an essential energy source, and the other type, cholesterol, is essential for cell membrane, bile acid, and steroid hormone production. Cholesterol in the lipoprotein's core is esterified. Unesterified, or free cholesterol, is enveloped in an outer phospholipid monolayer. Woven around and through the exterior layer are proteins called apolipoproteins. New data are proving these apolipoproteins to be more influential in lipoprotein metabolism than was ever previously recognized. The function of apolipoproteins falls into four categories. They are involved in assembly of lipoproteins, provide structural integrity, serve as co-activators of enzymes, and act as receptor ligands for cellular uptake. The unique collection of apolipoproteins on each lipoprotein surface indicates its origin, function, destination, and ultimate fate. For example, in the intestine, apolipoprotein B48 is involved in assembly and packaging of ingested triglycerides and cholesterol into chylomicrons. ApoB48 also provides this large, very triglyceride-rich lipoprotein with structural support. ApoE serves as the ligand for hepatic uptake of the chylomicron. Additional apolipoproteins, such as C2 and C3, may be acquired to regulate triglyceride metabolism. particles remaining after triglyceride release, referred to as chylomicron remnants, retain ApoB48 and ApoE. ApoE is essential for hepatic uptake. In the liver, VLDL is assembled with apolipoprotein B100. ApoB100 provides structural integrity to VLDL and serves as a ligand for cellular reuptake. ApoE is another ligand for reuptake. As with chylomicrons, the additional apolipoproteins C2 and C3 may be acquired to regulate triglyceride metabolism. The smaller particle resulting from VLDL metabolism, IDL, retains ApoB100 and ApoE for receptor reuptake. The even smaller LDL, a remnant of IDL, retains only ApoB100. It is important to note that the lineages of particles just discussed all have ApoB in common, whereas HDL, the particle involved in reverse cholesterol transport, features ApoA1 as its primary structural apolipoprotein. ApoA1 also plays a role in enzymatic reactions. In addition, HDL participates in carrying ApoA2, ApoE, ApoC2, and C3. These are referred to as exchangeable apolipoproteins because they readily transfer back and forth between HDL and the ApoB particles. Revelations about the unique combination and function of the apolipoproteins on each particle are continuing to advance our knowledge of lipoprotein dynamics and the distribution of their cholesterol and triglyceride content. Accordingly, our evaluation of fasting plasma lipids continues to evolve. Over the years, guidelines have shifted from the measurement of total cholesterol and triglyceride content of lipoproteins in the plasma to a more refined focus on LDL, the bad cholesterol, which deposits excess cholesterol in the arterial wall, and HDL, the good cholesterol, which retrieves cholesterol from the arterial wall and returns it to the liver. While LDL is clearly recognized as the major atherogenic particle, new evidence indicates that increased levels of other triglyceride-rich lipoproteins, including IDL, VLDL, and chylomicron remnants, also contribute to cholesterol accumulation in the arterial wall. Together with LDL, these atherogenic lipoproteins are defined as non-HDL. In patients with a predominance of non-HDL, triglycerides are elevated, and in these patients, current guidelines recommend the calculation of non-HDL cholesterol, which reflects the bad plasma cholesterol from all atherogenic lipoproteins. Non-HDL cholesterol is equal to total cholesterol minus HDL cholesterol. Furthermore, it's important to remember that non-HDL and HDL can also be distinguished according to apolipoprotein content. For example, ApoB100 and ApoB48 are unique to non-HDL, whereas ApoA1 is unique to HDL particles. As the science progresses, the routine measurement of plasma apolipoprotein concentrations may guide clinicians into even more sophisticated decisions regarding dyslipidemia diagnosis and management.